Good evening, everyone, and welcome to our very special program with the team from the Event Horizon Telescope. I'm James Monroe. I'm the producer of adult programs at the Museum of Science Boston, and I'm thrilled to be here tonight and to introduce our special guests. Back in 2017, we had the pleasure of hosting Shep Doleman and the Event Horizon Telescope team here live on site at the Museum of Science for a wonderful conversation where they talked and shared all about their research and work in attempting to capture the very first photo of a black hole. And just 2 years later, in 2019, their success was seen on a global stage as that very photograph swept news headlines all around the world. And tonight, I'm so thrilled to welcome Shep back to the museum, virtually of course, and he's joined by several other members of the team, and they're going to talk about what it took to get that photograph, the work that they've continued to do since its release, the future of the program, and of course, the importance of the global science collaboration that made it all possible. And tonight is a part of our current virtual winter-spring season of adult programming at the museum. We are nearing the end of our season already. Next week, we have our final 2 programs on Wednesday night and Thursday night. So they're both wonderful, and I encourage you to go to our website at mos.org/adults to check out details on both of those and sign up for your spot in both of those as well. Now, I'll be back a little bit later on tonight for a Q&A with our speakers. So as you have questions come to mind, you can submit those at any time by going to slido.com and entering the code Event Horizon Telescope, all one word, just as it appears on your screen right now. Once again, that's Slido, SLIDO.com, with the code Event Horizon Telescope. Now, I need to thank our friends from the Lowell Institute for their continued support of the adult programming here at the museum. It's because of them that we are here tonight and that this event is free for all of you. So please join me in giving a huge virtual round of applause and thanks to everyone at the Lowell Institute. And finally, after the talk tonight, I ask all of you to consider going to donate.mos.org/mosathome and make a gift to allow us to keep bringing free virtual programming just like tonight into all of your homes. Once again, that's donate.mos.org/mosathome. But now it's my privilege and pleasure to welcome to the stream our very first special guest of the evening, the founding director of the Event Horizon Telescope, Shep Doleman.
Okay, thank you very much, James. It's a real pleasure to be here with all of you virtually. When I came here last time, we had not yet imaged the black hole, and I'm very happy to say, as I think everyone knows, that we were able to do it. So it was a time of a little bit of tension, and now it's a great time of relief and answering some of the questions that we've always posed and now can answer. So simply put, the Event Horizon Telescope is this visionary project to take the first photograph of a black hole. And more than that, to study black holes. We wanted to turn the black hole boundary into a natural laboratory so we could ask questions about fundamental astronomy, fundamental physics, some of the deepest questions we can hope to ask and answer. And it's difficult in 2 ways. One is the black hole really tries with all of its might to remain hidden. It is cloaked by nature's gravity, so we really can't see all the way to the heart of the black hole itself. And secondly, technically, it's just very, very difficult. So it's been a huge odyssey, a huge voyage, and our team is going to tell you a little bit about the secrets behind how we made this image tonight. I think we all know what black holes are. Simply put, they are a concentration of matter that's so massive and it's small enough so that its gravity is so intense that even light can't escape. So how do you image something like this? Let's go to the next slide. To motivate this, I want to show you this galaxy called Hercules A, and you're seeing it in optical light, the way your eyes would see it on a clear night. And it's about 2 billion light years away from us. Now, if you look at it in the radio waves, in the next slide, you see something really extraordinary. You see these jets of near light speed material streaming from the center of this galaxy. And the only thing that we know of that can power this would be a spinning supermassive black hole that weighs about 4 billion times what our sun does. And that from the north and south poles stream these charged particles that light up the way you see it here. And that's shown in the next inset. So magnetic fields are twisted in the gravity of the black hole, and they launch these charged particles, and they can stream for over 1 million light years. So black holes are ferocious engines that light up the night sky. And that's shown in the next slide. So here's how black holes work their magic. If you were to drop an apple onto the ground, it would release enough energy about a joule of energy to power your cell phone for 1 second. But if you compacted all of the Earth's mass into a black hole in the next slide, and you drop the apple now onto an object that was the same mass of the Earth, but just reconfigured, it would release 10 to the 16th, or 1 with 16 zeros behind it, amount of energy, of joules. And that's enough, in the next slide, to power all of Manhattan for an entire year. So just reconfiguring matter allows black holes to be these tremendous engines of redistribution of energy on galactic scales. So let's go to the next slide. So this is going to show you why we can hope to see the shadow of a black hole. Light from all around the black hole is twisted into these geodesics, or the path that light takes around the black hole, and you wind up seeing a very clear and unmistakable feature. You see a circle of light, which is where photons or light orbits the black hole in a circle, and you see some surrounding light, which is lensed emission from all the hot gas that's trying to get into the event horizon. And the next slide, you'll see that Einstein's equations predict a very precise form for the size of this black hole. If you know the black hole's mass, you know exactly the size of this ring. So one of the great goals of the Event Horizon Telescope was to measure that ring and verify Einstein's theory of gravity in the one place in the universe where it might break down, the edge of a black hole. Next slide. So this is exceedingly difficult because the size of these objects is very, very small. So for Sagittarius A star, the supermassive black hole in the center of our Milky Way Galaxy, it's about 50 micro arc seconds in angle, which is equivalent to seeing your favorite citrus fruit, a tangerine or an orange, on the moon. So we have to build a different kind of telescope to see it. And that's shown in the next slide. So if you want to measure something that's really, really small, you use this very simple relation in astronomy. And the smallest size you can see on the sky is determined by the wavelength of light that you're observing, in our case, radio waves, divided by the size of the telescope. But you also need to be able to see through the Earth's atmosphere. You also need to be able to see through all the interstellar gas between us and this black hole. And you need to see through all the hot gas that's madly trying to get through the event horizon. So there are many gauntlets that light has to run through before it gets to our telescopes on Earth. So we need to observe at a wavelength of light that's about 1 millimeter. That's the Goldilocks wavelength that can traverse all of those different hurdles. And when you go through this formula, you realize you needed to build a telescope that's 10,000 kilometers in extent, and that's clearly impossible. So how do we do this? Next slide. So a normal telescope operates in kind of a standard intuitive way. It has a shaped surface, like the one you see on the left. Light bounces off this shaped surface, comes to a point at the focal point, and that's where you put your camera. So it geometrically combines all the light that it collects into a single point. We kind of can recreate that in radio waves using something called interferometry, which is shown in the next slide. So the way the Event Horizon Telescope works is we link telescopes around the globe, network them with atomic clocks, and then you see the next slide. You see that the different telescopes receive radio waves from the black hole. And the next slide, we record them using atomic clocks that lose about 1 second every 10 million years. And the next slide, I think you'll see they get recorded onto hard disks, just like the ones you have on your home computer. And then the magic of it is in the next slide, we bring it all together using UPS trucks and FedEx at a central supercomputer called a correlator, which then combines them to give us a telescope as though we had a telescope as large as the distance between these radio telescopes. Next slide. Now, thankfully, the Earth rotates. So if we only had 2 such telescopes, we would only be able to get essentially 1 bit of this virtual mirror that's the size of the Earth. But as the Earth rotates, all of the telescopes in the Event Horizon Telescope Array give us a little bit of information. And over the course of an evening, it sweeps out this virtual mirror that you see on the right. And we get enough information to begin to make our images. Let's go to the next slide. So in April of 2017, magically, everything came into focus, and all of our telescopes were ready to go. I say magically, but it required the hard work of hundreds of people, hundreds of experts around the globe. And for 1 week, we experienced some of the best global weather ever, and we were able to light up the entire array to make our first image. And go to the next slide, please. And here it is. I'm not going to bury the lead. We were able to measure and image this black hole. So M87 is a very interesting galaxy, and this black hole lies at the heart of M87. In the upper left, you see these jets of material streaming from the center of this galaxy. You see one on the right because it's coming towards us. And in the same way that a train whistle is higher in pitch when it's coming towards you, the one on the right that's coming towards us is very bright. There's also one on the left, which is Doppler deboosted, so we don't see that. But we see how it impacts the intergalactic medium because there's this cloud on the lower left. And then as we zoom in by about a factor of 10,000, we always see this same jet. We can't really see the engine that's driving it until we made this image with the Event Horizon Telescope at the very bottom, which showed this telltale ring of light that we'd been postulating we would see for many decades. So this was the realization of a great dream of the entire team and a way to test Einstein's theory at this boundary. And the last slide shows you just how big this gargantuan black hole is. Everything you know, our entire solar system, even Voyager, the farthest person-made object from the sun, easily fits snugly into this black hole. So if you didn't feel small and isolated with this pandemic, this is not going to help. But now to tell you more about how we made the observations, Sarah Issaoun from Radboud University.
Thank you, Shep. So I'll be telling you a little bit about how we got together in 2017 to take the data and take you through the journey of the whole data until it's ready for imaging. Next slide. So I'll give you a little look of our telescopes. So if you look at them closely, you'll notice that they're actually all different. We used 8 telescopes during our 2017 campaign at 6 different geographic locations all across the world. But all these telescopes were actually designed for completely different science. They were designed to work as a single telescope. They were not designed to be linked together to make an Earth-sized telescope. What we did is actually borrow them because they happen to be at just the right places where we could make this virtual mirror come together. And they are at very high and dry sites, at some of the most dry places, deserts in the world. And the reason for that is because the atmosphere between us and space absorbs our signal and scrambles it. So we need telescopes at sites where we have very little water vapor in the atmosphere and a very stable atmosphere, so no turbulence. Next slide. So although they look all different, they have something in common. It's what we call our Eht Backend. It is our recording equipment. You can see on the left here. All our telescopes are equipped with the exact same equipment that records our precious data. So what this equipment does is digitize our data into digital packets and records them onto these boxes, which we call modules, that are filled with stacked helium hard drives. During our campaign, we used about 92 individual modules or 736 hard drives. We recorded a whopping 3.5 petabytes of data. That's about 3,500 standard laptops of data. During our 2017 campaign, we had a 12-day window where we had to observe, but because of the atmosphere, weather is such an important factor in our decision-making. We had 5 observing days to trigger through our entire campaign, and we had to decide on which day to do it. So we paid very close attention to weather patterns, to current and forecasted weather at each of the telescopes, and decided which are the best days to trigger. As Shep mentioned, we had actually pretty amazing weather that is very atypical of whenever we observe with the EHT, and we were able to trigger 5 days within about an 8-day window. Next slide. So of course, during the campaign, on top of operational staff that are at the telescopes, we also staffed the telescopes with EHT observers, with our EHT members who travel to these sites and act as local experts on our Eht backend, our recording, and on the telescopes themselves. So here are some nice pictures from our 2017 campaign with all our amazing EHT observing staff and operators. So I'll take you to Arizona, where I was observing for the Eht campaign. Next slide. So here are some pictures of what it's like to observe in Arizona. On the left here, you can see our Eht backend in Arizona. It's very much like the rest of the Eht backends at all the different telescopes. It has little blinking lights on the modules, which tell you that it's recording our precious EHT observations. There's some pictures of the control room and a receiver room where we cable up our backend to record our data. Nice pictures of the telescope. And you can see these boxes here, packed boxes, are actually our modules after we are done recording, where we pack them up and then drive them down the mountain to get shipped via UPS or FedEx to the correlation facility. Next slide. So all our shipping in the EHT, be it our equipment that needs to go to the telescopes or our precious modules, go through this man, Don Souza. He used to be a policeman for the state of Massachusetts, and now he takes care of all our shipping in the EHT. So Don makes sure that all of the modules, all of the precious data go where they need to be. On the right here, you can see our modules. You can see they have little red stickers on them, which means that they're full with our precious data. And these modules are ready for correlation. Next slide. So our entire data pathway is pretty impressive with the EHT. So from correlation, from the raw data, which is about 3.5 petabytes, to the image, which you can send on your phone, which is just a few kilobytes, we undergo 12 orders of magnitude in data reduction, which is a pretty extreme path to take. So let's go through it. Next slide. So the precious modules get shipped to 2 different correlation facilities where 2 supercomputers combine the data. Half the data goes to MIT Haystack Observatory in Massachusetts, and the other half to the Max Planck Institute for Radio Astronomy in Bonn, Germany. Next slide. So at correlation, all of the signals from each telescope get combined such that we are only left with the signal that the telescopes see in common. So telescopes that are closer together tell us about the large scale structure in the image. Telescopes that are further apart tell us about small scale structure in the image. However, at correlation, we cannot model what the atmosphere does at each telescope, which actually mess up, scramble our signal. So in order to actually combine the data and increase our signal, we need to model this atmosphere. And this is done at the calibration stage after correlation. Next slide. So the calibration stage is actually a pretty important stage and the one that took us most of the time to get from the data recorded to a publication of our image. It was a 1.5-year process of many feedback loops from correlation to a data calibration team that would model instrumentation effects and atmospheric effects on the data via 3 independent pipelines, and then go through cross-checks and then go back to correlation until we had a product that was good enough and well understood enough to pass to imaging. Next slide. Also, we have to understand our telescopes, not just our data. So our telescopes are completely different from each other, and understanding how they work, what exactly are the instrumentation effects from the telescopes that contaminate the data is a very important step as well of the calibration. So we needed to really understand every aspect of the telescopes in order to remove these effects and only be left with the source signal, the signal from the black hole. Next slide. So this is what it looks like for a radio astronomer, our final data. So this is basically signal seen by different pairs of telescopes. So from the left are signals seen from telescopes that are close together, and then all the way to the right are signals seen from telescopes further apart. And you'll see it has this kind of bounce shape. And this bounce shape for a radio astronomer, and for me, when I first saw this in 2018, was the most beautiful picture I had ever seen, because it already tells you something really exciting. And what it tells you is that for a ring, a uniform ring on the sky, the shape that this kind of data would have is also a bounce. And you can see it in this kind of gray dashed line. Another interesting thing that this data reveals, next slide, is that there's part of the data that don't really match this kind of bounce. And you can see that it's split into 2 levels. This tells you that one direction of the telescope see more signal than another direction. This tells you that there is an asymmetry in the ring. And what this asymmetry tells us is that the ring is actually asymmetrical in the north-south direction. So already just from this data, a radio astronomer, like all of us at the EHT being super excited to get to image, saw this data and already kind of knew and was hoping to see an image. So next I'll pass on to Daniel Palumbo, who will tell you how we get from this data to an actual image that we shared with you all. Thank you.
Awesome. Thank you, Sarah. Hi there, folks. My name is Daniel Palumbo, and I'm a Harvard grad student in astronomy. I'm here to talk to you about imaging a black hole. And at the top of my slide, I've got pictures of the news after our first big result, the first image of a black hole, because this is a scientific problem that is deeply connected to the way we, as humans, perceive images as reflections of objective truth in nature. We're not just setting out to produce a sensible measurement of some physical quantity. We're trying to convey to the scientific world and to the public what we have seen when we looked into the heart of a galaxy in as honest and understandable a way as possible. Next slide. For that reason, I would describe this as both a scientific and philosophical problem, stemming essentially from the fact that our data don't completely pin down exactly what we saw. So as Sarah said, our data is a sparse sampling of something called the Fourier transform of the image. You can think of our problem as trying to piece together a song that no one's ever heard before being played on a piano with half the keys missing. On the right, I'm showing a tiny fraction of the possible images identified by EHT algorithms as possibly fitting the data. And despite the fact that they are different in how blurry or sharp they are, they're similar in their ability to generate the same signal on our instruments as what we saw in April 2017. And yet, we've highlighted a few in green as preferred, and it will be my job here today to convince you that we haven't completely fooled ourselves in the way that we've selected some images over others and concluded that we're seeing a ring that's brighter on the bottom than the top. Next slide. So there's essentially two philosophies for solving this problem. The first is an inverse modeling philosophy, which has a long history in radio astronomy. This approach takes the data and essentially runs the optics backwards. This blurry waffle you see here corresponds to something called the dirty image. It's what you get when you just invert the raw samples of our data with zeros everywhere else. And it's not a coincidence that it looks almost like crests in ocean waves viewed from above. The underlying math is the same. It's one of interference of waves. And each of our data points is essentially measured as a frequency of a wave. So software like diffmap runs an algorithm called clean, which just subtracts peaks out and tries to identify a simple distribution of blobs on the sky that could describe our data, and is designed so that these blobs are of the same size as our array resolution. So you can watch this algorithm run if you press next slide. You'll see it clean up to a simple ring of blobs. And this blurriness is nice if you want to guarantee that you aren't overfitting your data by adding structures that nominally your instrument could not have resolved. So this is exactly as blurry as we think our telescope is, our Earth-sized telescope. However, there is also the forward modeling philosophy, which is an incredibly general approach in which, given some description of possible images, you can propose some distribution of light on the sky, generate the data that our telescope array would have seen, and score these proposed images or models one at a time based on the agreement between that generated synthetic data and what we actually observed. So if you had some parameterized model of images of geese, this approach would tell you which image of a goose best fit the data. Now, the best image of a goose will still be a bad fit overall, but you can still find the most likely or maximum likelihood image of a goose if you wanted to. For imaging, rather than images of geese, we use a very general model, which is just a grid of pixels, and we sample possible images to find the best fit, and people spend their lives building tools to sample efficiently. Next slide, please. So for the image of M87 that we all know and love, there were three algorithms used to produce images. The first, diffmap, as I said before, is an inverse modeling approach, while EHT imaging and SMILey are both forward modeling approaches. Now, as you might imagine, given those gaps in the data that we saw before, there are lots of ways to help fill in the gaps in where we just don't have telescope spacings to sample information. And in each of these algorithms, there are a number of extra knobs and settings and user choices we can tune to change preferences and how those gaps are filled. These control things like smoothness and contrast. And though ultimately the data has the final say, there's wiggle room in all of these algorithms that are enumerated here. And we don't need to get into the details, but in the next slide, when choosing what values of all of these parameters to use, we want to make sure that we aren't biasing ourselves towards making images that have big holes in the center of a bright ring, because that would be very exciting and it would be very indicative of a black hole, but we don't want to trick ourselves into seeing something that's not there. So we take the same sampling, the same telescope positions at the exact same time each night, and we generate synthetic data of simple geometric models of a ring, a crescent, a disk, a pair of blobs, and we make images using every combination of parameters in a wide range on each of these models, independently optimizing each of our algorithms for a known underlying image. So to return to the piano analogy, we're using the same piano with the same missing keys to play songs we already know, to understand how best to fill in the gaps while also understanding our biases. Next slide, please. So what I find to be the most important test is if we optimize our imaging algorithms to produce the best possible images of a flat disk and then transfer those optimized parameters to the MED7 data and run the same problem, we still cannot help but get a ring that's brighter in the south. So this is a big hint that we're not tricking ourselves. So next slide. Now for our final image, we ultimately train on each of these simple models and find preferred parameter sets that do well no matter what true image lies beneath, and then use those to make our final image. This is an indication that no matter how we try to break our code, we can always find some parameter space that's good no matter what, and we trust those more than others. Next slide. So now we have our best image from each algorithm on each day. We are faced then with the question of how to compare or even combine them into a single consensus image from the EHT. The forward modeling methods, pretty visibly in this image, tend to produce slightly sharper images, though the overall morphology is the same, of a ring brighter in the bottom. When we, as a collaboration, return to this question of context and the caution appropriate to searing the first image of a black hole into the collective cultural consciousness, we chose to blur all of our images to the resolution of the array, so that we aren't filling in any finer structures than we nominally resolve with our sharpest capabilities, essentially the largest separation in our telescopes. Next slide. So here are the April 11th images. So at this resolution, where we've blurred everything to be just as blurry as every other method, our images look remarkably similar and carry the same qualitative information, which ends up being very physically rich. It's a ring brighter on the bottom. And these can be readily combined with simple averaging in the next slide. So now we have consensus images on each day of observation. And even here, we as scientists make a choice in what image we emphasize in public engagement at talks like this. Typically, we show the April 11th image because it's a day where essentially all of our telescopes were working great and had nice weather. We have great data. Next slide. Now, about a month ago, the EHT released the first polarized images of MED7, here displayed 2 ways on the same 4 days. And though the underlying data is significantly harder to work with and the underlying physics is much more rich, the philosophy is much the same. We train multiple algorithms on a range of synthetic models and test problems and combine the best possible parameter sets from all of them to get cautious but meaningful images that are rich with insight into the underlying physics. If you take one thing from this talk, let it be this. Throughout the experimental sciences, there is no concrete notion of an exact objective truth. It is unreachable beneath experimental uncertainties or incomplete data. And so the job of a good scientist, or in this case, hundreds of good scientists and technicians and engineers, is to let the data speak for itself wherever possible, and otherwise be clear and honest with the choices that are made in handling data so that you believe your own work, so that others believe your work, and ultimately so that others can repeat and prod at and check your work. And so far, the EHT results have remained pretty solid. So with that, I will hand it off to Richard and Nantua, who's going to tell you about how we go from images to understanding the underlying physics of the MED7 black hole and the hot plasma that surrounds it. So Richard, take it away.
Thank you, Daniel. And it's great to have the opportunity to bring EHT science to such an incredible platform as the Boston Museum of Science. I'll be unveiling what we learned about near-horizon physics through the interplay of observation and theoretical modeling using simulations, and giving a preview of the path ahead. The first example we investigate is M87, which is a prototypical case of a jet accretion flow black hole system that has a prominent jet, and it hosts the first shadow imaged by the Event Horizon Telescope in 2019 and in polarized light in 2021. So let's go to M87 in the next slide. And if we go next, the constellation Virgo at 12 hours of right ascension when the movie starts, and 13 degrees declination, houses the best studied cluster of galaxies, the supermassive black hole with the second largest angular size in the sky, resides in Virgo, roughly 2,000 times the distance to the galactic center. The Virgo cluster galaxy that houses this black hole is Messier 87 or M87, which Heber Curtis described as a curious straight ray, as you can see, due to its relativistic jet. M87's jet extends 100 kilolight year in radio and has been observed throughout the electromagnetic spectrum, most recently by the Event Horizon Telescope in polarized light. And in the next slide, we'll start to understand how the polarization structure connects to the magnetic fields. So the polarization direction in this figure of the jet at different scales is represented by stripes, and it's typically perpendicular to the direction of the local magnetic field. At the 1,000 light year ALMA scales you see on the upper left, the polarization is ordered only on scales that are smaller than the bright spots in the unresolved core. We can go closer in to the insets at 43 gigahertz at very long baseline array scales, where we see disorder from magnetic field turbulence and Faraday rotation. And if we go even further in at 230 gigahertz Event Horizon Telescope scales, both on the bottom and on the right, we see that the polarization actually makes an ordered and azimuthally spiraling pattern in a patch of coherent emission that's on the southern bright spot. So if we go to the next slide, we can further connect polarization to understand what the magnetic fields are doing. The polarization is oriented at what we call the electric vector polarization angle in the ticks in these figures. The radial case of the electric vector polarization angle on the left corresponds to a toroidal magnetic field or a ring symmetric magnetic field. So that's an indication of what we call standard and normal evolution, where the fields basically just bend to the whims of the flow. In the middle column, we have an azimuthal and ring symmetric electric vector polarization angle pattern. And this corresponds to radial magnetic fields. And on the right, we have the spiral electric vector polarization angles that correspond to vertical magnetic fields. And vertical is parallel to the axis of the whole rotation, the symmetric system that's going out of the page. And this is a case where the fields are very, very much resistant to the flow and what we call dynamically important. And we can see more of this dynamics in the next slide. So at the heart of M87, there is this 6.5 billion solar mass black hole that's feeding on billion-degree plasmas that are accreting onto it and being launched around it. So we can try to compare simulations on the right. So go next. It's both unblurred, which is the simulations, which can have arbitrarily high resolution. And on the bottom, we see blurred cases where we actually incorporate those instrumental effects that Daniel was talking about before me. And using a library of simulations like this, we could try to understand some of the physics that goes into heating the particles that are glowing. So the particles that we're talking about tend to be electrons and protons. And in the model whose formula you see describing the ratio of ion to electron temperature ratios, which we call the R beta model, because next it depends on the plasma beta, which is the gas pressure of the magnetic pressure. There is a behavior in which the ion to electron temperature ratio is low at low beta, which is gas or magnetic pressure, and the ion to electron temperature ratio approaches R high, or the high value of the ratio, at high beta. And trends in this model parameter space for R low equals 1 include having, if you look on the right in this simulation library, the brightness asymmetry tends to increase as we increase the magnitude of the spin. And this is an effect that is known in special relativity due to Doppler boosting. So the angle relative to the black hole, which we call the viewing angle that we're looking at these images at, is just 17 degrees from the axis for M87. So we're practically looking down it, but not quite. And you can see some of this relativistically beamed asymmetry in especially the high spin cases. And there are also trends in which that the magnetically arrested disk simulation tend to have the more spiral electric vector polarization angles. And that implies a vertical and dynamically important field, which tends to be more consistent with our observations. But in the simulation library, we have some less compatible standard and normal evolution simulations in which we have radial electric vector polarization angles and a roughly toroidal implied magnetic field. And in order to try to pinpoint where the emission's coming from, if you look at the panels on the left, we note that there are, looking at vertical slices of this that contain the simulation axis, we have jet regions and disk regions. So the jet regions are nearer the rotation axis, and they have lower values of the beta, or the gas over magnetic pressure. So the magnetic pressure is dominating in the jet regions. The disk regions are closest to the equatorial plane. So in those 4 panels, the equatorial plane is basically a horizontal line going through the middle of these. And the R high is low case, it corresponds to electrons in the high beta disk or equatorial regions having high electron temperature, or the disk dominating the emission. But when the R high is relatively high, we have the electrons in the disk region having relatively low electron temperature. So the jet regions dominate. So we can pinpoint these effects of electron thermodynamics in our simulations, but the observations aren't yet detailed enough to distinguish between those 2 cases. And the simulations can tell us something about the magnetic field strengths, so that we trust the magnetically arrested disk scenario a lot more to correspond to the observations in this when we compare the simulation library to the observations at M87. But it's still a work in progress to understand where the electrons are being heated. And we can also use similar techniques to try to understand what we believe will be the black hole at our galactic center, Sagittarius A star, which we haven't resolved yet because it's hard to take an honest look at this picture of such a rapidly varying system. It's as if M87 is like a Great Dane chasing its tail, and Sagittarius A star is like a Chihuahua chasing its tail. And you're trying to take a picture of both, but the Sagittarius A star case still confounds us. So in the next slide, we'll start trying to understand Sagittarius A star. So we're trying to understand the near horizon regions, and when I say near horizon, go next. It's a Milky Way galaxy that we know to be 100 kiloparsecs or 300 kilolight year in diameter. It's surrounded by a halo of dark matter, and it contains about 100 to 400 billion stars. The Earth is about 8 kiloparsecs from the galactic center, and we're still zooming in, and we can zoom in. We don't quite see a prominent jet like we did in the M87 galaxy, but the innermost parsec of the galactic center actually hosts stars that pass very close, and what we're going to see as very eccentrically around a central object. So these stars are being perturbed by some probably very, very compact region that we infer to have 4 million solar masses. So if there were a black hole there, which we strongly suggest next, its structural radius would be 410 millionths of a parsec. So remember, we came out from 100 kiloparsecs, and now we're at 410 millionths of a parsec, or about 7% of an astronomical unit. And if we go next, we've actually have observations from the gravity collaboration of infrared flares at about 6 to 10 gravitational radii or half short-tail radii from the black hole. And we have a question next. We're trying to address with simulations. It's what happens there. So if we go next, we turn to what simulations have to say about the future of Sagittarius A star near the horizon. And probing electron temperature heating mechanisms such as turbulent heating models, which are the left two, and also models in which we convert magnetic to particle energy, which are the right two, we see that there's wide morphological differences both across heating mechanisms and within them. So the first types of heating mechanisms were the turbulent heating class, and they're similar to the ones that we use from 87, but even within this class, these time averaged images on the top row are showing very, very different morphology. So this is in the vertical plane, it contains the axis of rotation, and we see the special relativistic effects when we see the very, very asymmetric images on the left. But still, a turbulent heating model in the type 2 class has less asymmetry, and we see more of the outline of the outflow. And then we see a thick torus of disk emission that's lensed around the black hole. So you're actually seeing the disk that's behind the black hole being lensed around it in the type 3. And in the type 4, you actually see the extended outflow in those latter models that are governed by converting magnetic energy into particle energy. And we can also think about variability, which is our Achilles heel when it comes to Sagittarius A star next. So we can actually use simulations to make movies at a cadence that replicates the light crossing time of Sagittarius A star's gravitational radius, or 20 seconds. So with these movies that are framed of 100 gravitational radii per frame next, we can actually see some of the variability. And in the next one, we see these turbulent heating model variability tends to be the greatest and the best matching the observations. And the variability tends to be governed by the brightest features that are moving around them. But if you go to the next movie, you actually see that there's just a pulsing of a fixed bright spot, and that has the least variability in all these models. And in the next movie, there is some variability, but the brightness contrast isn't as much. And those latter two models have the least compatible variability with the observation. So with this preview, we can at least tell what we anticipate might be the physics that's governing Sagittarius A star. So in the next slide, you can imagine what the latest in the results that EHT will have based on these previews. But for now, you can check our official website for the recent results of multi-wavelength campaign. So the right column in the middle, you can see M87's jet with very different frequencies and different collaborations, from the East Asian VLBI network to the Fermi Large Area Telescope to EHT, which are, we like to be different, so we have the ring-like images. We can also see some of the results of using our telescope to test gravity by the ring sizes on the bottom right. We can also note that in the bottom row in the middle, that the position of the bright spot actually changes from year to year. So we were just talking about a few days in the earlier parts of this talk, but it actually changes a lot from year to year. And there's another jet on the left, which we came out and we saw the nearest to the horizon footprints of this jet in the very, very variable 3C279 galaxy. So in the next slide, we have our social media, and you should all be following it. It's free. You'll get more content, including this feed. And Nick Conroy, who who gives us lovely Crazy Bridge movies like this, is doing a great job with helping me cultivate this. So we need more followers like you, especially, Boston Museum of Science is very, very, very top level science critics. And I will turn to Carrie Hayworth for what's really next.
So thanks a lot, Richard. So I'm Carrie Hayworth, and I work on the instrumentation for the EHT, and I've got the exciting job to tell you about what's coming next. So, I see the black hole as an incredible achievement, but I also like to see it as the start of something, not the end. So there's a lot more to be done. I'm going to talk about the science that we're going to be hunting for next. But being an engineer, I also want to talk to you a lot about the technology challenges that we're going to have to overcome to make this science happen. Next slide, please. So we have an image of the black hole now, but we know we can get more out of it. Black holes aren't blurry, they're not stationary. The simulation on the right is what we think we'd see if we had the perfect equipment. So we want to make better equipment. We want to make movies because we want to capture that spin you're seeing. And that jet, if you remember, that Shep showed in his slides, we want to understand how that's connected to the black hole because we want to see it. We want a sharper image, but finally, we want to be able to study more black holes. So let's look in detail at a couple of these aspirations. Next slide. So Sagittarius A star is a black hole at the center of our galaxy, and it has light moving around it at small time scales. So we're talking around 20 minutes. So this is a simulation on the left and what we think we're going to be able to reconstruct from our data on the right. So as you can see, we're going to be able to study the flares and the spin. And this is a really important part of what we want to be looking at. Next slide. So M87, another black hole, is a lot further away. That's the picture that you've seen. It doesn't spin nearly as fast, but if we get some better resolution here, it means we are going to be able to see how the jet forms. Again, there's a model on the left and what we think we're going to be able to reconstruct from data. So next slide, please. So now we get to the part of how are we going to do this? So remember, Shep mentioned a virtual mirror. And so the more we can fill in this virtual mirror, the better. And what we need more telescopes. The more it's filled in, the better image we're going to be able to see. There's black lines, we see that up there in the right image there, for how much data we're getting with the array today. Now, if we doubled the size of the array, the blue lines are the additional. So you can see it is quite a difference. So right now we're looking all over the world to find new sites for telescopes. The blue names that you see on the world map are the ones that are already in the EHT, and the red ones are potential sites. The atmosphere, how easy they are to get to, and the baseline length or the distance to the existing dishes are all really important considerations. Next slide, please. So what are some of the challenges? Well, one good piece of news is that by working with large sites like ALMA, we can get enough sensitivity so that dishes all over the world don't have to be 50 meters. In fact, they can be more like 10 meters, and that's a lot cheaper. It's a lot easier to build. So it's easy, except for sort of. So I've highlighted in red a few items that I'm working on right now because they're items that are going to need new technology. So first, the scientists want more data. This makes sense. Think about it when you take a picture. The bigger the size is in megabytes, the more details that you see. Well, we're talking petabytes in this case. We're talking 20 billion pictures. We need to capture data at 256 gigabits per second, and that's 4 times what is being done in the current array. And we need to process it, and we need to record all of it. Each site, remember we're talking over 20 sites, but each site will have 3.4 petabytes of data. And that's going to end up being quite a lot of data we need to process. So Sarah mentioned that engineers and scientists go out to the telescope during a campaign. Now, it's getting a little bit harder to do if we go and double the sites. We don't have people that go everywhere. So we're going to need a sophisticated centralized software monitor control system so we can make sure that the telescopes are pointed in the right direction, that they're collecting data without having to have experts at every site. And so working on the speed, working on this amount of data, and working on better software are all things that I'm doing in order to bring new science. And so the team isn't just looking at the ground. And the reason we're not just looking at the ground is because Earth has some limitations, okay? It's a great place to study black holes, but we cannot increase the size of the Earth. So the longest size between the 2 telescopes is the size of the Earth. But if we go out to space, we can make a longer baseline. We also can't speed up the Earth's rotation. But when we go out to space, we can kind of simulate going faster. We've also got the Earth's atmosphere in the way, and that's great for breathing, but we can't observe all the frequencies that we'd like to see. So a satellite extension of the array, so putting one of these telescopes out into space, can overcome some of these limitations. Next slide, please. So longer baselines, more baselines, higher frequencies is what we're looking at for. Next slide, please. So one of the concepts that we're considering is the low Earth orbit satellite. So this is a satellite that orbits relatively close to Earth. It goes around Earth once every 90 minutes. So as you can see on the right, it can fill in data much faster than the ground array alone into our virtual mirror. And so what this is going to do is help us create movies of Sagittarius A star. Next slide, please. Another idea is to put a satellite in a geosynchronous orbit. Now, what that means is if you consider the Earth being right here and you have the satellite kind of stays in the same place as the Earth rotates. So as you can see, that's not going to create a lot of baselines, but it's going to create a really long baseline. So because the satellite is so far away, as Sarah said before, long baselines give us the ability to see small scale structures. We can study the ring of photons, and that'll give us a really precise measurement, even more precise than what we've had so far, of the black hole size. This great resolution is also going to allow us to study black holes across cosmic time, which I personally find just incredibly exciting. Next slide. But of course, space is also hard, right? We have a lot of technology challenges here. So two of them are on Earth, as Sarah described, we collect these petabytes of data. We put them onto a plane and we take them to a correlation center. We can't do that in space. We can't fly to the satellite, get it, and bring it back. So we need to have a cutting edge free space optical system. And what that is going to do is allow us to downlink as quickly as we take the data. So we're going to get it in at 256 gigabits per second and send it down to Earth as fast as we can take it. Another challenge is that all the telescopes need to be on the same time. They need to be synchronized. And the way that we do this on Earth is we use a maser. Well, masers are the size of refrigerators. We don't want to put those in space. It's really costly to get refrigerators into space. So we have to think of a smaller, more clever solution in order to be able to have the satellite in space. So there's quite a lot to do. There's quite a lot to learn over the next decade. And I want to thank everybody for being here. And I hope you will stay tuned as we discover more about black holes. I'm going to turn it back to Shep before we go to Q&A.
Hi, everybody. Well, I think that as you've seen, this was a visionary project. It still is a visionary project. And more than that, it required the expertise and the dedication of a very, very large team. There is a saying that if you want to go fast, go alone. And if you want to go far, go together. So in the very beginning of the EHT, we needed to go fast. We needed to do test observations. And we did those on a very small array. But to build out the imaging array, we needed to draw upon the expertise of people around the globe. And it was truly a global team that made a global telescope in every sense of the word. So hats off to the entire EHT team. And we are just emissaries of this much, much larger group. So going to the next slide, I think one of the things that astounded us was the truly human dimension to this problem and to this result. And I think Daniel touched on this. When we came down from our hotel rooms on April 11th and we saw this picture on the front of every major newspaper across the world, we realized that it had resonated with everyone. We had uncovered something that we thought was invisible. We had done something that people thought was impossible. And when you do that and you work with cherished colleagues and you nimbly sidestep the boundaries of the political realities that separate us, you realize that there's a lot that we can do together as humans on the planet. And as we come to grips with this horrible pandemic, as we come to grips with the larger issues that we need to solve globally, I like to think, and our whole group likes to think, that the Event Horizon Telescope is kind of a light. It's a suggestion that we can come together and solve the hardest problems. It's been very inspiring for us, and we hope it's inspired you too. And now we're happy to answer any questions that you might have.
Thank you so much, Shep. Really inspiring final words to end the formal presentations on. Thank you for that. We are going to jump into a live Q&A with our entire panel while we're waiting for them all to pop back up on the screen and be together, Brady Bunch style. Once again, I'm James Monroe. I'm the producer of adult programs at the Museum of Science Boston. If you have a question for our panel and you have not submitted it yet, you still can by going to slido.com and entering the code Event Horizon Telescope, all one word, just as it appears at the top of your screen right now. Before we do jump in, I just want to thank the five of you for taking so much of your time over the past couple of weeks and preparing this really incredible evening of presentations. The work is just fascinating and so important and so inspiring, and we are just so appreciative of all of you for taking time and allowing us to share this with our audiences. Questions are rolling in, so we're just going to jump in. The first question, we kind of touched base on it, but they're asking if you have plans on generating images of other black holes in the future, and if there are any that are on your short list, and why. So who wants to take that one? Shep?
Well, I'll take that one.
Great.
So first of all, we love Sagittarius A star, the black hole at the center of our Milky Way galaxy. We're also in love with M87, the 6.5 billion solar mass black hole that's 55 million light years away. If we had to be trapped on a desert island with two black holes, those would be the ones we would choose. That being said, there are other targets. They are smaller in angular size, so they are more difficult to image. But as Carrie said, we're making progress with increasing the angular resolution of the Event Horizon Telescope, increasing its sensitivity. So we hope in the coming years with this next generation instrument that we're designing and building to see perhaps up to 10 additional black holes that we can study to test Einstein in new ways.
Amazing. So updates to look forward to for a future program when we can get the 5 of you actually on site here at the museum and hear about all of those. A very specific question. Why does Sagittarius A star not have heated streams flying outward?
Well, it depends on what frequency you look if you're trying to find how powerful the outflows are. If you actually turned on gamma ray ice, which Event Horizon Telescope isn't in the business of doing, but telescopes like the Fermi Large Area Telescope are, you'd actually see enormous bubbles that are plus or minus 10 kiloparsecs from the center of the galaxy in the direction that you would expect jets to be in. So there may have been activity about 10 million years ago from the active galactic nucleus that is Sagittarius A star that actually energized particles to create bubbles in gamma rays, which have different emission mechanisms than the synchrotron radiation that we see at the Event Horizon Telescope scales that we can see the jets in M87. But we still have a very uncertain picture as to what exactly is powering the outflows from the galactic center at several frequencies, including gamma rays, and whether or not there actually is a powerful outflow, because it might depend on the frequency. Sorry, it might depend actually on the viewing angle. There might actually be a powerful outflow in radio that might be pointing towards us that we don't really see at the orientation that we're sitting at.
Thank you, Richard. A couple questions about the James Webb Telescope and if that could ever help your team gather necessary data in the future.
Daniel, do you want to tackle that one?
I don't think anyone in the wide world of astronomy should comment on the timeline for James Webb, but it's also in a somewhat different frequency regime for us. So I think it has tremendous utility, particularly for sort of smaller mass black holes and understanding sort of optical regime. But for our studies, it's a particular type of problem where you need to be able to see down to the heart of a black hole that I don't think JWST is in range to do, just from a sort of spectral point of view.
Thank you. So, Shep, you touched base a little bit of this at the end with your final remarks, but just wondering what some of the challenges are that have come up when working and collaborating with such a large team, but also teams that are located at sites all over the world. You touched base on a little bit of like how you sidestepped political differences. I'm just wondering, and so is the audience, what some of those challenges are and how you all have navigated through so successfully.
Yeah, it's a great question. So this is a big collaboration. We're a big family. And as with any big family, we have disagreements around the dinner table, as they say. But one of the ways we tried to address this was with what I call creative tension. As a few of the speakers alluded to tonight, we used multiple ways of addressing problems in the project. So we had different ways of crunching the data. We had different ways of imaging the data. And instead of down selecting, instead of saying one group or one method was better than another, which could create some tension and division, we used all three of them, as I think Daniel showed very, very well, together so that everybody's effort was seen in the final results. And in this way, we were able to check our results, but at the same time, everyone saw the fruits of their labor in the final result. And I think we navigated some disagreements in the collaboration by using this general philosophy. That's one way in which we were able to work together as a team.
Yeah, and when thinking about, the past year that we've had, and it's just been such a model for what can be achieved when people work together in science. And so I hope that that's been an inspiration for others in the industry and in STEM in general that have, and Sarah's back. Welcome back, Sarah. Over the past year, it just has really resonated with me of the power of teamwork and the power of bringing as many brilliant minds together as possible from all over the world. So speaking of COVID, some questions about how the past year has been for the research and for the work, and if the pandemic has sort of affected all of the work with the Event Horizon Telescope or slowed anything down. I don't know, Carrie, if you have any insights on that.
Well, we've certainly had to be more creative about how we're going to get things done. I basically had a kitchen table absolutely covered with equipment and trying to, probe things, over spaghetti sort of thing. And so at first it kind of blindsided us all. And then we kind of said, okay, how are we going to work this out? And so, we sort of did a hybrid approach. A lot of people brought things home. We learned how to communicate over Zoom. We learned how to, point the cameras and say, well, what do you think, looking at this? And so, it's all about, you have to be creative in this job anyway. And so, yeah, I threw another wrench into the situation, but I think that we actually all came out of it with a lot more tools than we went into it with. And I think that's actually just a testimony to the people that we've been working with.
And Sarah, how about you? Because you're based in the UK, correct? So what has this experience been like for you during the past year?
I'm in the Netherlands.
The Netherlands.
Yes. It's been tricky, but I think since we're a big collaboration anyway, it's impossible to have us in one place in any case, even in normal circumstances. But I think for us, we already had a way of working, remotely and communicating, so it didn't feel like the work was affected that much, apart from, of course, everybody's personal, effects that the pandemic had on them. So I think the one thing that I do miss is, of course, going to a telescope and observing, which we had an observing run a couple months ago. And usually I'm at the telescope, and this was the first time that I was supporting remotely, and I definitely do miss the mountain. And I do miss, of course, seeing our colleagues, and it is definitely much easier to get work done and to be productive when we're all in one place. So this was kind of a challenge.
Thank you both for those insights. Shep, a question about where people can get the print of the M87 image that you have on the wall behind you.
Oh, wow. Well, a check for $1,000 or money in a paper bag dropped outside my house will get you one of these. But if you wanted to print one out on a laser printer, you should be able to go to the EHT website. It's www.eventhorizontelescope.org, and I believe that in the press tab there, you can find this high resolution image, and one can download it and print it.
Great. So
we also have these wonderful little pins.
I know if we were on site.
I'm not sure if I have one here, but we're swag challenged, so we absolutely need some more swag, and we hope to get that soon up on the website. Pins, brooches, you name it.
Great. Some questions about asking if you can explain the exact methods used to reduce that many bits of data to a small picture that can fit into our phones.
I guess I can take this one.
Great.
I The exact method is averaging. So we don't actually get rid of any data apart from at the correlation stage where we only keep the signal that the telescopes see in common and get rid of the noise that are at the individual telescopes. From that point on, everything is just averaged. So we try to smooth the data so that we can combine and average it down. We average it in time and in frequency and boost up our signal. In the imaging process as well, when we had images from different methods, we averaged them together to form the images that we have per day. So I think that is the way to get from that point to a few kilobytes. And of course, the entire process in between means that you need to understand every single effect and remove it before you can average, which is a lot more complicated, and it took us a lot longer to get there. But essentially, averaging is the way to do it.
Thank you, Sarah. What advice do you all have for amateur astronomy buffs at home that maybe want to keep engaging with the Event Horizon Telescope? How can people stay involved who are sort of amateur astronomy fans?
Well, we have social media. We have Facebook. We have a Twitter. We have an Instagram. If you down the road want to join, you could you get a PhD in astronomy. Okay, I'm kidding about that. We were looking to grow our social media. We're looking to make connections. So definitely look us up, follow us. We're usually very receptive to questions and new members. And I see Daniel was about to unmute himself.
Yeah, sorry, if I can add something when you're done. Yeah. Oh, well, sure, okay. Yeah, so I just want to add, sort of in the spirit of people prodding at and reproducing results, all of the scripts and the data that we used for our initial results in 2019 are online. Wow. If you just Google like Event Horizon Telescope imaging scripts, you'll probably get there pretty quickly. And so as long as you know how to install Python, which is a programming language, you can at home play with the data, make the images. You will see these rings appear as you run our scripts, and you can make whatever parameter choices you want or write your own model fitting code or whatever, and you can muck about it with all the same headaches that we did. So if you want to sort of skip the degree and just go right to the images, that's an option.
I love that. And speaking of a degree, we do have someone out there who has been following the work that you all have been doing for several years now, and the EHT was instrumental in pushing them to pursue a BS in astronomical and planetary sciences. So they're wondering, actually, Richard, back to sort of your joke, is there any current EHT research at an undergrad, that an undergrad like this person can get involved in? So anyone that is currently studying, is there a way for them to get involved in your work?
Well, we actually do have at various EHT institutions, including the Harvard-Smithsonian Center for Astrophysics, where I work, a number of different places where mentors can directly interface with Event Horizon Telescope members. So depending on what your institution is, you may already have people who are doing Event Horizon Telescope science. And I mentored an undergrad last year. I actually started a program that interfaces with the National Society of Black Physicists, and we actually had a couple of interns who were undergrads / master's students, and there are literally 300 Event Horizon Telescope members throughout the globe in different universities. So probably you should go and look at our website, look at our papers, look to see who's on them, look to see who's doing things that are relevant to the type of skills you bring to the table, and reach out to people. I mean, usually they're searchable by their Google Scholar. Usually they have archive preprints, usually have their emails on personal websites. So depending on where you are and how your interests and skills align with what we're doing, follow our research, reach out to individual members, and maybe you can start collaborating virtually.
And I want to add a promotion that engineers are also welcome as students, because there's a lot of engineering to be done. There's electrical and there's mechanical, there's software, and so certainly a student who is saying, well, I don't really want to be an astrophysicist or get a PhD, but I'd really like to help out, and I do engineering. This is something you could get a hold of me, and I'm pretty easy to find too.
Can I just also add that what Richard said is really true, that you can just contact anybody, because that's how I got started. Oh, wow. I contacted my current PhD advisor when I was an undergrad looking for just a random project to learn about astronomy. I didn't even know about EHT or imaging black holes or anything. I just wanted to do something cool. And I just took a shot and emailed a bunch of professors, and someone responded, and now I'm here. So, just, go for it, take risks, share your skills and say what you're interested in. And I'm sure someone, if they don't have something for you, they'll definitely recommend someone else to contact. So it's definitely, worth a shot.
All great advice.
Can I add something to that, James?
Yes, please.
I want to point out that this has just been a ton of fun. It's the most exciting project that I've ever worked on in my career. I think I'm by far the senior statesman here, and that's important, because early career people, undergraduates, graduate students, and postdocs played huge roles in this project. We simply couldn't have done it without the creativity and the dedication of all the early career people. Everyone you see here, started out as undergraduates, graduate students, postdocs, and there's always a place to do some daring and amazing science, no matter what your career stage. So, as Sarah said, encourage everyone to jump out and take some risks, to jump off cliffs, invent parachutes on the way down.
I love that, and that's a perfect way, I think, to wrap the night. Before we go, though, any final remarks from any of you for our audience? Anything that they can stay tuned for?
Does someone want to say something about maybe what's coming next? Or?
I mean, if we're allowed to be cryptic, I would say that the most exciting physics is yet to come, I think, in terms of what the EHT will unravel. But
that's a great way to leave it.
I love that cliffhanger.
Can we say the word Sagittarius A star?
Well, now you said it, so
now I said it. Yeah.
Yeah. So we're hoping that other results will come out soon, but soon is kind of a relative term. The other thing that's important is that we want to be able to tell the story in exactly the right way. I think you've seen from all of the presentations here that great care is taken when we analyze the data, when we image the data, and when we interpret the data. And the only way that we can really do that is by maintaining some level of secrecy. So we have working groups that analyze and work through all these issues and ideas. And only when we all agree, or when there's basic agreement, do we then announce the results. So when they come, you can be sure that they've really been thought through. And we hope to get some new results sometime this year.
I love it. I love ending on that teaser note, which only means that there's still a lot more, obviously, to come from these five and their entire team. And we hope here at the museum that we can continue to be a part of sharing that work and your research with the audiences and the public. So I look forward to our next event with all of you back on site here at the museum when it's safe to do so. Thank you to the five of you so much again for taking the time to share all this with us. Thank you again also to Nick Conroy, who's a part of the EHT team, who worked so hard behind the scenes in pulling this together with us. So huge kudos to him. And thank you to our friends at the Lowell Institute for making tonight possible. And thank you to our audience for watching and spending your Wednesday night with us. We hope you will do so again next week as we wrap up. As you leave the virtual theater tonight, details on our next program for next Wednesday night will pop up. We hope to see you then, but until then, stay safe, stay well. Have a wonderful night, everyone. Thank you so much.
Bye-bye. Thank you.
Yeah, thank you. Thank you, audience.